In mathematics, the lexicographic or lexicographical order product is a generalization of the way the alphabetical order of words is based on the alphabetical order of their component letters. Definition: given two partially ordered sets A and B, the lexicographical order on the Cartesian product A times B is defined as if and only if A less than A, or the result is a partial order. If A and B are each totally ordered, then the result is a total order as well. The lexicographical order of two totally ordered sets is thus a linear extension of their product order. More generally, one can define the lexicographic order on the Cartesian product of n ordered sets, on the Cartesian product of a countably infinite family of ordered sets, and on the union of such sets. Motivation and uses. The name of the lexicographic order comes from its generalizing the order given to words in a dictionary or encyclopedia. A sequence of letters A1, A2, AC appears in a dictionary before a sequence B1, B2, BK if and only if at the first I where I and by differ, A comes before by in the alphabet. That comparison assumes both sequences are the same length. To ensure they are the same length, the shorter sequence is usually padded at the end with enough blanks. This also allows ordering of phrases. For the purpose of dictionaries, etc., padding with blank spaces is always done. See alphabetical order. For example, the word Thomas appears before Thomson in dictionaries because the letter A comes before the letter P in the alphabet. The fifth letter is the first that is different in the two words. The first four letters are Tom in both. Because it is the first difference, the fifth letter is the most significant difference. A lexicographical ordering may not coincide with conventional alphabetical ordering. For example, the numerical order of Unicode code points does not always correspond to traditional alphabetic orderings of the characters, which vary from language to language. So the lexicographic ordering induced by code point value sorts strings in an unambiguous canonical order, but it does not necessarily alphabetize them in the conventional sense. An important property of the lexicographical order is that it preserves well orders of finite products. In particular, if A and B are well-ordered sets, then the product set A times B with the lexicographical order is also well-ordered. The lexicographical order also preserves the Noetherian property. The lexicographical product of two Noetherian relations is again Noetherian. An important exploitation of lexicographical ordering is expressed in the ISO 8601 date formatting scheme, which expresses a date as YYYYMMDD. This date ordering lends itself to straightforward computerized sorting of dates such that the sorting algorithm does not need to treat the numeric parts of the date string any differently from a string of non-numeric characters, and the dates will be sorted into chronological order. Note, however, that for this to work, there must always be 4 digits for the year, 2 for the month, and 2 for the day. So for example, single-digit days must be padded with a 0 yielding 01, 02, 09. Another generalization of lexical ordering occurs in social choice theory. Consider an election in which there are 4 candidates A, B, C and D. Each voter expresses a top-to-bottom ordering of the candidates, and the voters' orderings are as follows. The Minimax voting method is a simple Condorcet method that counts the votes in a round-robin tournament and judges each candidate according to its largest pairwise defeat. The winner is the candidate whose largest pairwise defeat is the smallest. In the example, the largest defeat of A is by D, 65% rank D over A. The largest defeat of B is by D, 65% rank D over B. The largest defeat of C is by A, 67% rank A over C. The largest defeat of D is by C, 68% rank C over D. Minimax declares a tie between A and B since the largest defeats for both are the same size, 65%. This is like saying Thomas and Thomson should be at the same position in an alphabetical order because they have the same first letter. However, if the defeats are compared lexically, we have the min-lix-max method. With min-lix-max, because the largest defeats of A and B are the same size, their next largest defeats are then compared. A's next largest defeat is none. B's next largest defeat is by A. 51% rank A over B. Since B's next largest defeat is larger than A's next largest defeat, min-lix-max selects A. This makes more sense than the min-max tie, since a majority rank A over B. A finishes ahead of B given min-lix-max for the same reason that Thomas is ahead of Thompson in an alphabetical order. Another usage of the min-lix-max principle in social choice theory can be found in the ranked pairs voting method. Although ranked pairs is usually defined by a procedure that efficiently constructs the order of finish, the result of that procedure is equivalent to finding which of all possible orders of finish is best according to a min-lix-max comparison. In this case, any two possible orders of finish can be lexically compared by looking at the majorities on which the two orders disagree. To see which of the two orders reverses the largest of those majorities, that order is the worst of the two. In the example above, the ranked pairs order of finish is ABCD. ABCD affirms the majorities who rank A over B, A over C, B over C and C over D, and reverses the majorities who rank D over A and D over B. The largest majority reversed in ABCD is 65%. The only other ordering that doesn't reverse a larger majority is BACD, which also reverses 65%. ABCD is a better order of finish than BACD because the set of majorities on which ABCD and BACD disagree is the majority who rank A over B, and BACD reverses the largest majority in this set. Note that the min-lix-max method is not equivalent to ranked pairs, even though both use a min-lix-max principle. Ranked pairs satisfies the independence of clone alternatives criterion, the Smith criterion and the Condorcet-Loser criterion, and other criteria failed by min-lix-max. Here is an example that shows min-lix-max and ranked pairs are not equivalent. Suppose there are 4 candidates A, B, C, D, and suppose the 6 pairwise majorities are 56% rank A over B, 55% rank B over C, 54% rank C over A, 53% rank A over D, 52% rank B over D, 51% rank C over D. Min-lix-max selects D. This violates the Condorcet-Loser criterion because majorities rank all 3 of the other candidates over D. The ranked pairs order of finish is ABCD, which has D in last place. All other possible orders of finish are worse than ABCD on ranked pairs min-lix-max comparison. For instance, suppose we compare ABCD with DABC. The majorities on which ABCD and DABC disagree are the 3 majorities that rank A over D, B over D, and C over D. The largest of these 3 is the 53% who rank A over D, and that majority is reversed by DABC, which means DABC is worse than ABCD. Suppose we compare ABCD with the min-lix-max order of finish DACB. The majorities on which ABCD and DACB disagree are the 5 majorities that rank B over C, C over A over D, B over D, and C over D. The largest of these 5 is the 55% who rank B over C, which is reversed by DACB, which means DACB is worse than ABCD. Case of multiple products. Suppose as an n-tuple of sets, with respective total orderings, the dictionary ordering of is then that is, if one of the terms and all the preceding terms are equal. Informally, represents the first letter, the second and so on when looking up a word in a dictionary, hence the name. This could be more elegantly stated by recursively defining the ordering of any set represented by this will satisfy where to put it more simply. Compare the first terms. If they are equal, compare the second terms, and so on. The relationship between the first corresponding terms that are not equal determines the relationship between the entire elements. Unlike the finite case, an infinite product of well orders is not necessarily well ordered by its lexicographical order. For instance, the set of countably infinite binary sequences is not well ordered. The subset of sequences that have precisely 1 does not have a least element under the lexicographical order induced by 0 less than 1 because 100,000 greater than 01000 greater than 001000 greater than is an infinite descending chain. Similarly, the infinite lexicographic product is not Noetherian either because 011111 less than 101,111 less than 110,111 less than is an infinite ascending chain. Groups and vector spaces. If the component sets are ordered groups, then the result is a non-Archimedean group, because e.g., n less than for all n. If the component sets are ordered vector spaces over R, then the result is also an ordered vector space. Generalizations. Ordering of sequences of various lengths given a partially ordered set A. The above considerations allow to define naturally a lexicographical partial order over the free monoid A** formed by the set of all finite sequences of elements in A, with sequence concatenation as the monoid operation, as follows. If is a prefix of or, and where is the longest common prefix of an, and are members of A such that, and are members of A**. If less than is a total order on A, then so is the lexicographic order less than D on A**. If A is a finite and totally ordered alphabet, or asterisk is the set of all words over A, and we retrieve the notion of dictionary ordering used in lexicography that gave its name to the lexicographic orderings. However, in general this is not a well order, even though it is on the alphabet A. For instance, if A equals A, B, the language A n B, n0, has no least element. Less than DAAB less than DAB less than DB. A well order for strings based on the lexicographical order is the short-lec order. It is however not Noetherian. The short-lec order can actually be defined as a lexicographic product of two orders: the ordering of strings by length, and the union of orders of finite string of every size with some order. Similarly, it is also possible to compare a finite and an infinite string, or two infinite strings. Comparing strings of different lengths can also be modeled as comparing strings of infinite length by right-padding finite strings with a special value that is less than any element of the alphabet. This ordering is the ordering usually used to order character strings, including in dictionaries and indexes. Quasilexicographic order. The quasi-lexicographic order on the free monoid A over an ordered alphabet A orders strings firstly by length, so that the empty string comes first, and then within strings of fixed length n, by lexicographic order on them. Another generalization: consider the set of functions f from a well-ordered set x to a totally ordered set y. For two such functions f and g, the order is determined by the values for the smallest x such that f(g). If y is also well-ordered and x is finite, then the resulting order is a well order. As already shown above, if x is infinite, this is in general not the case. If x is infinite and y has more than one element, then the resulting set yx is not a countable set. See also cardinal exponentiation. Alternatively, consider the functions f from an inversely well-ordered x to a well-ordered y with minimum 0, restricted to those that are non-zero at only a finite subset of x. The result is well-ordered. Correspondingly, we can also consider a well-ordered x and apply lexicographical order where a higher x is a more significant position. This corresponds to exponentiation of ordinal numbers yx. If x and y are countable, then the resulting set is also countable. Example: monomials. In algebra, it is traditional to order terms in a polynomial by ordering the monomials in the indeterminates. Such matters are typically left implicit in discussion between humans, but must of course be dealt with exactly in computer algebra. For example, for testing the equality of polynomials. More specifically, the definition of Grobner bases and their computation are heavily based on the choice of an ordering of the monomials. To define such an ordering, one identifies every monomial with its vector of exponents, and one chooses an ordering on these vectors of integers. This ordering must satisfy some further conditions to be admissible for Grobner bases. See monomial order for details and the admissibility conditions. One of these admissible orders is the lexicographical order. Another one is the total degree order, which consists in comparing first the total degrees, and then resolving the conflicts by using the lexicographical order. More generally, every admissible order may be defined as the lexicographical order on the values of a set of n linear forms with real coefficients applied to the vector of exponents. Decimal fractions. For decimal fractions from the decimal point, a less than b applies equivalently for the numerical order and the lexicographic order on the digital representations, provided that strings with a recurring decimal 9 like 399,999, and strings with trailing zeros are omitted. With these restrictions, there is an order-preserving bijection between the numbers and the strings. Colexicographic order. The colexicographic or colex order is a natural order structure of the Cartesian product of two or more ordered sets. Given two partially ordered sets A and B, the colexicographical order on the Cartesian product A times B is defined as if and only if B less than B, or the result is a partial order. If A and B are totally ordered, then the result is a total order also. More generally, one can define the colexicographic order on the Cartesian product of n ordered sets. Suppose as an n-tuple of sets with respective total orderings. The colex ordering of is then the following is an ordering on the three-element subsets of, based on the colex ordering of the triples obtained by writing the elements of each subset in ascending order. 123 less than 124 less than 134 less than 234 less than 125 less than 135 less than 235 less than 145 less than 245 less than 345 less than 126 less than 136 less than 236 less than 146 less than 246 less than 346 less than 156 less than 256 less than 356 less than 456. Colexicographical ordering is used in the Kruskal-Katona theorem. Reverse lexicographic order. In a common variation of lexicographic order, one compares elements by reading from the right instead of from the left, i.e., the rightmost component is the most significant, e.g., applied in a rhyming dictionary. In the case of monomials, one may sort the exponents downward, with the exponent of the first base variable as primary sort key, e.g. Alternatively, sorting may be done by the sum of the exponents, downward.